Alright, so we're going to finish up chapter 3 today. Alright, and this is where we're going to be doing some true stoichiometry. And I'm not really going to go through how to balance an equation. That's pretty simple. I just want to stress the fact that, ladies and gentlemen, at no point during anywhere in this school year should you ever be working with an equation that you have not balanced. Okay? There is never going to be a time where it's okay to have an unbalanced equation. Right? So if you come across an equation in a problem that is in your textbook or I've given you, if you already see coefficients written in there, you may assume that it is balanced. I am never going to trick you, nor will they do this on the AP exam, where they only partially balance it and they are waiting to see if you notice that it's not really balanced. That's never going to happen. Okay? If you see coefficients, you may assume it is balanced. If you don't see coefficients, you should assume that it is not balanced and you need to do that. Oh, whoops, sorry. So those of you that have been my student before, this diagram should look familiar. But for those of you that were not, this is basically my flow chart of how to do any kind of stoichiometry problem. You will always have some given information and you will be asked to solve for some kind of unknown. And all I'm showing you here are the different units that you could be given or asked to solve for. So let's just review real quick. Tell me, how do you convert back and forth between number of atoms, ions, molecules, any of that into moles? What's your conversion factor, Rachel? You got it. Avogadro's number. And you can put the same thing over here as well. Okay? How do you convert back and forth between moles of anything and grams of anything? What's the conversion between grams and moles? Sean? Use your periodic table, the molar mass. I'm going to call it MM from the PT. Molar mass from your periodic table. How do you convert back and forth between a volume in liters and moles? What's the conversion for that? Yeah, Hayes. 22.4 liters. You got it. 22.4 liters, but I want you to make a note, and you said this, Hayes, make a note to yourself, that conversion factor is only okay to use for gases only. .4 liters, you can only use that conversion factor if you're dealing with a gas. And what I'm trying to show you in this diagram, folks, is that no matter what unit you are given, atoms, grams, liters, whatever, you cannot convert into your unknown without going through moles. Okay? You cannot go directly from atoms of a reactant to liters of a product in one step. You can't do that. If I gave you a number of atoms and asked you to solve for liters of some gas, this diagram also tells you how many steps that problem would be. That would be a 1, 2, 3 step problem. And again, I may put this in red because it is important. You cannot do any kind of stoichiometry unless your equation is balanced. One last thing that I want to fill in here if you're going from, let's say, moles of a reactant to moles of a product, this conversion right here, what do you use as the conversion factor? Where do those numbers come from? Yeah, Nick?
Is it the coefficients?
Yep. It's called the molar ratio, which is the coefficients from your balanced equation. Okay? So we're going to now do a couple of just very basic stoichiometry problems. You can use this diagram if you wish, or you can use a method that you are more familiar with from your Chem 1 class, whatever. Okay? So, what I want you to do, you're going to do these problems on your own. Second one is a little bit more challenging than the first. Okay? But let me just introduce number one, and then I'll have you do it on your own. Number one says, how many grams of each reactant are needed to produce 15 grams of iron from the following reaction? So folks, 15 grams of iron is my given information. My unknown, in this particular problem, is actually two problems in one. Okay, so what I would suggest to you, because this is two problems in one, start by using the 15 grams of iron will lead to how many grams of iron oxide. That's one problem. Do a second stoichiometry conversion. 15 grams of iron will give you how many grams of aluminum? And folks, is this reaction balanced? Nope, you need to balance it. So this is just some practice with stoichiometry. If you finish number one and you're feeling pretty confident, go on to number two. Number two is a little bit more challenging, but I think you can do it. Try it out. In case you had not noticed, if you've gotten to number two, I have not given you a chemical reaction, but there is one. So I'm going to just get you started on this one. Number two says we have a piece of aluminum foil and we're given its dimensions. Length, width, and height, I guess. And just stop right there. From those dimensions, what can you get? Think geometry. Volume. Okay? And what unit would that volume be in? Centimeters cubed. Okay? So it says you're adding aluminum to some HCl. how many grams of H2 gas are produced? Well, aluminum foil plus hydrochloric acid, and the problem is telling us one of the products, and you can figure out that other product. Just look at these reactants, guys. What type of reaction is this? Single replacement. These two elements will be switching places. What, not the formula, but what by name will be the other product over here? If hydrogen is left by itself on the product side, what is the compound that will be here? Aluminum chloride. Think about charges. What is the formula for aluminum chloride? AlCl3. Is that reaction balanced? Nope. Let's see. You take it from there. Remember how I told you to get used to using density as one of the earlier steps in a multi-step problem? This is what you have here. If your answer is a few decimals different, she got 3.09, that's okay. If your answer is 47.3, that's a little too far off. But yes, a little difference is okay. I will tell you all that this second question, number 2, is a very test-like question. Okay? Meaning that you're having to come up with the equation yourself. Okay, sometimes I'll give you a reaction, but usually I'm going to have you come up with it yourself. I give you enough information to figure it out. But also, if you'll notice in number 2, unlike number 1, I didn't just give you a starting value. You had to sort of figure out how to even get this starting given value to begin your stoichiometry. You had to do some calculations using density. I said it before, that is a very common thing in an AP Chem problem. So number 2, very much like a test question, in that it's not completely straightforward. Okay, anything? Let's talk limiting reactants. Okay, and let's define it first. Whether you have a reaction that has 2 reactants, 3 reactants, 4, 5, 50, it doesn't matter. however many reactants you have, one of them is always going to run out first. Folks, tell me what happens to a reaction. Even if you have 5 different reactants, if one of them runs out, what happens to the reaction? It stops. It's done. Okay? What do you call the other reactants, the ones that did not run out? Excess reactants. The ones that you have some left over. Okay? And I've put this statement in green because a limiting reactant problem, a calculation, differs from the ones that we did on the previous slide because a limiting reactant problem will not give you just one starting amount. It will give you amounts of maybe both of the reactants, or if there are 3 reactants, they'll give you amounts of all 3. That's how you know you have a limiting reactant problem, and not just a straightforward stoichiometry. Okay? If you are given more than one starting amount. And folks, there are different ways to solve limiting reactant problems. I am going to show you the way that I think is most useful in an AP class. Depending on who your teacher was, different teachers teach limiting reactant problems differently. Okay? I'm not saying that this way is the better way. This is just the way that's most useful for the kinds of problems you see in an AP setting. Okay? And instead of talking through these steps, I want to jump right to a practice problem. Okay? And I've said if you don't like this way, there is another way, which if we have some time, I will show you. But let's do this one together. All right. The question says, ammonia is produced by the following reaction. What mass of ammonia, that's this guy, what mass of ammonia can be produced from a mixture of 100 grams of nitrogen and 500 grams of hydrogen? Okay, let's answer that question first. We'll come back to this second question in a minute. First things first. Is the reaction balanced? No. So let's balance it. Alright? And I know that this is a limiting reactant problem because I have amounts of both reactants. And you might think, which one do you use? Do you go with the 100 grams of nitrogen or the 500 grams of hydrogen? The best way in an AP setting to answer these questions is you're going to use both of them. Okay? You are going to solve 2 separate stoichiometry problems. Let's start with the nitrogen. We are going to change 100 grams of nitrogen into grams of ammonia. We're going to do a 3-step stoichiometry problem. That is one possible answer to this question. Okay. What mass of ammonia can be produced? This might be the answer. In order to be certain about that, I have to do a second stoichiometry problem. And again, folks, you may have learned a different way to do a limiting reactant problem. this is the way that's going to be most useful in an AP setting. But if you like the other method, and you're more comfortable with that, that's fine. We're going to do the same thing, except this time we're going to start with the other reactant, but go to the same product. Okay, so we have two possible answers here. See if you remember this from Chem 1. How do you know which is the right answer? It's the smaller one. The smaller number is the correct answer. Okay. So how much ammonia can be made? The correct answer is 122 grams. Let me ask you a second question that is not written on the slide. Which reactant is the limiting reactant? Nitrogen. Okay? I want you to be very, very careful. When you're doing a limiting reactant problem, make sure you look at what the question is actually asking for. This particular question asked how much product can be made. So you should put a box around that number or circle it. But folks, sometimes you would be given numbers just like this, and instead of them asking which or how much product can be made, they will just say which reactant is the limiting reactant. You would still have to show all of these calculations. However, if the question says which reactant is the limiting reactant, don't put a box around this number. NH3 is not a reactant. If the question just says which reactant is the limiting reactant, N2 is the answer. That question does not have a number answer. Okay? And I'm telling you, it seems like a real nitpicky thing, but the AP graders are very picky about what you circle as your answer. If they say which is the limiting reactant and you circle this number, they're going to mark it wrong. They would give you credit for the work, but the answer would be wrong. You circled a number that is a product. You didn't circle the reactant. So if this is the limiting reactant, what's this? The excess reactant. And the second question here says, how much unreacted material remains? Another way to say that, how much hydrogen is left over? And I want you to just throw out some ideas. How do you think we could figure out, not yet how much is left over, how could I figure out how much H2 was used up? We know how much product was made, so let's take that 122 grams and do grams of ammonia convert to grams of H2, and the answer there will be how much H2 was used in the reaction. So that's how I'm going to choose to solve it. You may have thought of another way, and if we get the same answer, I'm happy. just to be clear, is that the answer to the question of how much is left over? No. What is that number? How much hydrogen was used? Well, let's look back at the original problem. We had, to start off, 500 grams of hydrogen. We used up this much. Round to 3 sig figs. That is how much hydrogen I had left in excess. Okay, so you had some questions on your summer assignment that asked questions about the excess. That's how to deal with that. Okay, our last topic is yield. Okay. Folks, you need to know the sort of the definitions, the meanings of the different types of yield. Okay? Theoretical yield. Right? And first of all, guys, actual yield and theoretical yield, you might want to make a note. Those are always going to be masses in grams. Actual yield and theoretical yield will always be a number, some mass in grams. Theoretical yield is the amount of product you would get if you had run this reaction and there was 0% error, which is impossible. Okay? And I want you to make another note. Theoretical yield, that whatever that number is, it will never, ever be given to you. You will always have to calculate theoretical yield using stoichiometry. That will never be given to you in a problem. Always have to calculate that one. Actual yield, again, a mass in grams, is the amount of product that you actually got. You ran this reaction in the lab. There was some error, as there always will be. Okay? Your actual yield is almost always going to be different from your theoretical yield. Tell me this. Would you expect your actual yield to typically be less than or greater than your theoretical? Less than. Not always, but it is usually your actual yield will be less than your theoretical. Okay? This is how you calculate percent yield. Easy to remember. A comes before T in the alphabet. Actual over theoretical. Okay, and remember I told you, I think it was last class, any type of percentage that you calculate, it's kind of a general rule. Percentages you may round to 1 decimal place. Okay. So, let's do a problem. I'm just going to introduce it to you, and then you're going to do it on your own. The question says, aluminum burns in bromine, producing aluminum bromide. That sentence right there is telling you the reaction. So actually, before we even read the rest of the problem, I can see that I have not been given a balanced equation. So let's come up with that before we even read further in the problem. How do you write aluminum by itself? Al is added to bromine. How do you write bromine by itself? Br2, good.
I got that one.
It's diatomic. It produces aluminum bromide. What's the formula? Very good. Is it balanced? No, let's balance it. Okay. Now let's read on. In a laboratory, 6 grams of aluminum reacts with excess bromine. Please do not be thrown off by that word. It's just telling you so that you don't even have to worry about it. It's telling you that aluminum is the limiting reactant and bromine is the excess reactant. Okay? This is not a limiting reactant problem. We have 6 grams of aluminum, so I'm just going to write that right there above the AL. 50.3 grams of aluminum bromide are produced. What is this number that they've just given me? Is it, what kind of yield is it? Actual. This is the actual yield. Remember, I told you, theoretical will never, ever, ever be given to you. You will always have to calculate that. And the question says, calculate the theoretical and the percent yield for aluminum bromide. Go. Percent yield is basically an indication of how good was your experiment. If you guys go on to take chemistry in college and you take the lab course that goes with it, for almost every lab you will do percent yield calculations, and some labs, if your percent is below a certain number, they will make you redo it. I want you to try this. I'm not going to lie, this problem, it's a beast. Try it. Once you read through it, it is not only a limiting reactant problem, it is also a percent yield problem. All put into one. Go! Do it! The final answer. Remember, if you're off by a few decimals, that's okay.